So, in the last lecture, we learned about order of magnitude and system of units. So, this is what we talked about last time, the seven fundamental units and what are the symbols. Let's move from here and talk about measurement of length, mass, and time. But first, since we are talking about all types of quantities, some very large, some very small, then we have some prefixes for very big measurements or very small measurements. Like you see here, deca. For big measurements, deca is 10. So 1 decameter would be 10 meters. 1 kilometer, kilo means 1,000. 1 kilometer is 1,000 meters. So kilo itself means 1,000. Hecto means 100. Kilo means 1,000. Megabyte, gigabyte, terabyte, you know that, right? Mega is million. Giga is billion. Tera is million. And similarly, we have peta and exa. Talking of small measurements, we have deci, that is 1/10, centi, that is 1/100th, like 1 centimeter is 1/100th of a meter. Milli is 1,000th, so 10 to the power minus 3. Micro is 1 millionth. Pico 10 to the power minus 12. Femto 10 to the power minus 15. Atto 10 to the power minus 18, etc. So be aware of these prefixes. So, what is the SI unit of length? The length is a meter, unit is a meter, but what exactly is a meter? Its definition has been changing from time to time, but see how precise it has been always. In 1889, meter was defined as the distance between two marks on a platinum iridium rod kept at 0 degrees centigrade in the International Bureau of Weights and Measures, Paris. So you have a rod and there are two marks on it. The distance between those two marks is a meter. So based on that, manufacturers went and produced meter rods and so on and so forth. Why 0 degrees? Why is there a mention of temperature? Because everything expands on heating and contracts on cooling. So we have to specify the temperature. And platinum iridium is a special kind of an alloy that doesn't change its characteristics, like doesn't get oxidized, and even its expansion, etc., is quite minimal. Then we redefined it in 1960 as 1650763.73 times the wavelength of a specified orange-red spectral line in the emission spectrum of krypton 86. Now, I know that all of this would be Greek to you, but let me briefly say that wavelength is a characteristic of a wave, that the distance between two successive crests, a wave goes like this, the distance between two successive crests or two successive troughs. And this is very precise because spectral line means when an atom de-excites, it sends out a wave. And the frequency of the wave is very precise. And the wavelength, therefore, is very precise because frequency, wavelength, and speed are related. And so many times that wavelength is equal to 1 meter. Very precise. And finally, in 83, we even redefined it as in terms of speed of light. The speed of light is written as c, which is nearly 3 into 10 to the power 8 meters per second. With this speed, the distance that light travels in 1 by 3 into 10 to the power 8 seconds is 1 meter. But it's not exactly 3 into 10 to the power 8, it is 299792458 of a second. The distance traveled by light in a very small time interval, which is 1 upon such a big number of a second in vacuum. So the point is, you see how precise we have always been in terms of defining that unit. There are subunits like centimeter, which is 1/100th, millimeter, that is 1,000th, micron is 1 millionth, nano is 10 to the power 9, angstrom is 10 to the power minus 10, written as A with a circle on top, and that is used in atomic physics. Fermi is 10 to the power minus 15 meters, which is used in nuclear physics. So purely based on convenience, we do use submeters of units, subunits of the meter, but the SI unit remains meter. Non-metric units of length are used in astronomy because we are dealing with very large distances, and it kind of becomes cumbersome to talk of such large numbers. Therefore, one unit in astronomy is the astronomical unit, that is the average distance between the Earth and Sun, which is of the order of 10 to the power 11 meters. Light year is the distance traveled by light in 1 year, that is of the order of 10 to the power 16 meters. 9.46 is more than 3.2. So this is of the order of 10 to the power 16. Parsec is of the order of 10 to the power 16 also. What is parsec? Earth goes around the sun in an elliptical orbit. The geometrical center of the ellipse, if I call A, and this E is the Earth, there's a point P at which the points A and E subtend a small angle of 1 second. Now, what is this second business? 1 degree is 60 minutes. Now, this minute is not the same thing as time, and 1 minute is 60 seconds. So, 1 second is 1 by 3600 of a degree. So, if it subtends such a small angle, then this distance P to, let us say, B is called 1 parsec. That is also used in astronomy. What is a SI unit of mass? It is kg, but what exactly is a kg? It is the mass of a cylindrical piece of platinum iridium alloy kept in that International Bureau of Weights and Measures. And also, mass of 1 liter of water at 4 degrees is also taken as 1 kg. But the definition of kg is this. Subunits are used. Gram is 1,000th of a kg. Milligram is 1,000th of a gram. That means 10 to the power minus 6 kilo. In atomic physics, we use AMU, atomic mass unit, or simply U, which is of the order of 10 to the power minus 27 kg, which is actually 1/12 the mass of a carbon 12 atom. Bigger units are used: quintal, 100 kg, ton, 1000 kg. In astronomy, we use solar mass as a unit, which is 2 into 10 to the power 30 kg, depending on the scenarios. This is all for convenience, and that was mass. And finally, let's talk of time. It is second, but how much is a second? At least length and mass you can see, you can feel, but second is very subjective. How do you measure it? Well, the solar day was taken as a standard, and that was divided in 24 hours, each hour of 60 minutes and each minute of 60 seconds. Therefore, one solar day is 24 into 60 into 60, that is 86,400 seconds, and 1 second is 1 upon 86,400th part of a solar day. The problem is, even the solar day has not been a constant. So scientists agreed that we will take a certain year as the standard. In 1956, scientists agreed to take 1900 as the reference year, in which the solar year was 365.2422 days, and 1 day is 86,400 seconds. So therefore, 1 second is 1 upon 365.2422 into 86,400th part of the year 1900. But now we have the best definition. In 1964, it was defined as a time interval of so many periods of specified energy change in the cesium 133 atom excites if you give energy, and it de-excites by releasing that energy in the form of a wave whose frequency is very precise, that really depends on the energy that you give. And the frequency of that wave is 9.19263,177 gigahertz. Therefore, the time period, frequency means number of cycles per second. Time period will be time taken for one cycle, that is 1 upon the frequency. So, second is, if you calculate the time period, the time period is 1 upon this f, right? So many time periods, if you add up, that will amount to 1 second. So that makes it extremely precise, the definition of a second. Other units of time, as we know, minute, 60 seconds, hour, 60 minutes, day, time taken by the Earth to rotate once about its axis, and one day is 24 hours, which is 86,400 seconds. Then we have month, which is on an average 30 days. Lunar month is the time for the moon to complete one revolution around the Earth, which is 27.3 Earth days. Year is the time taken for the Earth to complete one revolution about the Sun, which is approximately 365.2422 days. Now, this 0.2422 is approximately one fourth of a day. Therefore, every 4 years, we add a day to the year, making it 366, and that we do in February, as you know. February becomes 29 days. And that is called a leap year. Leap year, how do you find if a particular year is a leap year or not? If it is divisible by 4, it is a leap year. But then for century years like 1800, 1900, 2000, 2100, etc., the test is if it is divisible by 400, then it is a leap year. So 2100 is not divisible by 400, so it is not a leap year. You can check it out. Then we have decade, 10 years, century, 100 years, millennium, 1000 years. So there are various other units of time that are used for convenience purposes. So let's talk of some derived units. We have over 200 quantities and they're all dependent on those seven fundamental units. Area is length into breadth, so meter into meter, therefore symbol is square meter. Volume is length into breadth into height, so meter into meter into meter, meter cube. Density is mass by volume, mass is kg, volume is meter to the power 3. So kg per cubic meter. So we can write this as kg per cubic meter. That is all right, but we prefer to write kg than meter to the power minus 3. Velocity is distance by time, so meter per second, meter per second. Acceleration is velocity by time, velocity itself is meter per second makes it meter per second squared. Force is mass into acceleration, that is kg is mass and acceleration is meter per second squared, that is kg meter per second square, and that is given a name Newton to honor the scientist who did a lot of work in that area. Unit of work. Work is force into distance. Force is all of this, and distance is meter, so it is kg meter square per second square. That is given the name joule after the scientist called Joule. Power is work by time. Work is joule and per second, that is given a name watt. So if we divide this by second, then it becomes s to the power minus 3. Pressure is force by area. Force is Newton and area is square meter. Now Newton we already have kg meter per second square. If we divide further by square meter, it becomes meter to the power minus 1. And that is given the name Pascal, named after the scientist Pascal. Frequency is 1 upon time period, so 1 by second, and that is called hertz. Charge is electrical charge is current into time. Ampere is a fundamental unit. Ampere second, that is named after Coulomb. It is called Coulomb. And potential is work upon charge. So joules upon Coulomb, that is called volt in honor of Mr. Volt. So some units are named in honor of scientists who worked in that area, right? This is just some examples of some derived units. Now there are some guidelines in writing units. Symbol for a unit is written in small letters like small m for meter. But if the unit is named after a scientist like Newton, then it is written with the first letter in capital. For Newton, the symbol is capital N. We just write capital N for Newton, capital W for watt, and capital P and small a for Pascal. If it is named after a scientist, then the first letter will be capital. Otherwise, we write it in small letters. If you write the full name of the unit, then no matter what, it is always written in lowercase, even if it is named after a scientist. Example, small Newton, small j, joule, etc. If you write the full name of the unit. Then compound unit which are made by multiplication of two or more is written with a dot or a cross or a space in between. Example of a quantity is torque, which is force into distance. Force is Newton, distance is meter. So Newton dot meter or Newton cross meter or Newton's and as blank and meter. That's how we write that compound unit. Negative power is used preferentially like for velocities meter per second. And it is never written in plural. 10 meters is written as 10 m, not 10 ms. Even if it is plural, we write m only. These are some of the guidelines. Now let's do two small questions. The average mass of a uranium atom is 3.7 into 10 to the power minus 25 kg. How many atoms would be contained in 1 gram? And express it in order of magnitude. Well, let's write the average mass of a uranium atom in grams. This is in kg. In grams, if you want, then you have to multiply it with 1000. So it becomes 3.7 into 10 to the power minus 22 grams. That is the mass of one atom. So in 1 gram, number of atoms will be 1 divided by the mass of each atom. That turns out to be 2.7 into 10 to the power 21. 2.7 is less than 3.2. Hence, the order of magnitude is 10 to the power 21. Please appreciate this is a very large number. 10 to the power 9 is billion. 10 to the power 18 is billion billion. So it's really a very large number. In 1 gram, finally, the mass of an oxygen atom is 16 AMU. Find its order of magnitude in kg. Now, 1 AMU or 1 U is given to be 1.655 into 10 to the power minus 27 kg. It is 16 U, so multiplied by 16. If you multiply by 16, you will get this 26.48 into 10 to the power minus 27. But this is not in the standard form. Shift the decimal by one place, and therefore this you'll have to multiply with 10. So it becomes 10 to the power minus 26 kg, and that is also the order of magnitude. What is the order of magnitude of distance between Sun and Earth in kilometer? If light takes 8 minutes to travel this distance and the speed of light is given, so let's calculate the distance. Distance is speed into time, speed which is in meters per second, and time is actually 8 minutes, but we multiply by 60 to convert into seconds. So we have this is second that cancels, and we have so many meters. 1440 into 10 to the power 8 meters, but he's asking in kilometers. So divide by 1000. This 1440 will become 1.44 and meter will convert into kilometers. This is less than 3.2, so ignore it. And the order of magnitude is 10 to the power 8 kilometers. Right? So that completes this chapter. And now you should go and do all the questions in your school textbook in ICSE. I think this chapter is in ICSE. And after that, follow it up with the assignment that is there as a part of this course on the website.